Great. So today we want to talk about Price of Anarchy. That's an important one. But because before that, let's go and discuss the general idea of the class so far. Yeah. So we talk about some kind of stable solutions, Pareto optimal or Nash equilibrium or epsilon Nash. We will talk about others like, for example, correlated equilibrium, etc. But the catch is this one. In these stable solutions, the people may not get that much profit, essentially, or the overall profit or the utility that they will get, it might be less than some kind of coordinated move. You can always see, I mean, this is the level also you can, this one also you can think about in the philosophical sense, in a dictatorship versus democracy. So in some sense, when we talk about Price of Anarchy or Nash equilibrium, we are talking more about democracy. Each one is a selfish agent, try to do essentially the best for themselves, but there is no ruler essentially. But there is can have essentially a dictatorship. And in dictatorship, a dictator decides what is the best thing essentially. Or I mean, you can consider God, and some people say God says that, but it's anyhow the same thing. So that in some sense, and in the dictatorship things, I mean, you can just see, for example, the current thing in the like in the House or other things. So like I mean, the speaker is coming down because of some votes. This is in a dictatorship. This does not happen. So it means that there are some more efficiency in some sense. Versus here, that is more democracy, and I mean, this is the rules, and one person can essentially have some votes such that the Speaker of the House for the first time comes down. So then that's a democracy. So it would be chaos in some sense. And the question is that, I mean, there are some benefits. Of course, I mean, I think they are saying that democracy probably is the least efficient way of governing, except it is better than any other way in a long. So the same thing that we are talking here. So here we are talking about the Price of Anarchy. And the issue is that, yes, these guys, they are selfish agents. They somehow in a distributed way reach a settlement. But how bad can be, or how worse this can be comparing to the optimum solution that is given by God or by dictator or something like this. Like a good dictator, I guess. That he just tries to, or she tries to maximize the benefit of the people. And this is the thing that is called Price of Anarchy. So if you have anarchy, if there is no central agent, what is the price of it? Comparing to the case that we have essentially a dictator, a good dictator or God or something like this that decides that this is the best for us. Good. So that's the thing that we are talking about here. So let's just see some example. In the if you remember in the yes. So in the chocolate game that we had it, if you remember, we had this action that T3, T3. T3, what was that? You will get 3 and give it to the other person, and you will essentially 3. That was a carrot game, actually. Got the 3 carrots and give it to the other person. And that other person also take 3 carrots and give it to you. That was actually the one that provides the best outcome for everyone, because there, I mean, you could get essentially 6 carrots. Maybe if I was running it, it was not the best for me, but as auctioneer, but for the people, for the participant, that was the best. However, we discussed that if everyone wants to maximize his or her own utility, if we are in the selfish agent mode, and we try to essentially in a distributed way try to maximize the things, then in that case, the settlement or the Nash equilibrium would be T1, T1. Why? Because if this person is taking T1, like then like this is the first player, this is the second player, this is the Nash equilibrium. Why? because if this is a T1, T1, then the agent 1 does not want to change it, because if he or she changes from T1 to T3, then gets 0. Similarly, this is a symmetric game that we talk about it. So you can say the same thing also for player 2, that that player does not want to change it. So actually here, 1-1 is a Nash equilibrium. But 1-1, everyone only gets 2 essentially. So by choosing 3-3, we could get 3 times more total utility comparing to 1-1, which is a settlement case. So in some sense, we here you can define somehow the best outcome for everyone, and then try to see like how much we are losing in this equilibrium setting or Nash equilibrium, and that would be exactly the price of anarchy. Good. Okay, so let's define the best outcome for everyone. There are two ways that we can do it. So one thing which is you will hear a lot, essentially the best social welfare, or like they will call it the most efficient way, efficiency or social welfare. These are like the one that you hear a lot. And this is a given a strategy, like essentially you want to like for a first we need to define what's the meaning of welfare for a particular strategy profile. Again, the strategy profile is a vector of strategies, and each of them can be mixed or pure, of course. So if S is given to us, then the welfare, like the for this set of players, we have two things. One is the utilitarian function, which is the average expected utility. The other one is a egalitarian function, which is the minimum expected utility. These two are used a lot. Note that this average is essentially, this is equivalent of sum of utilities. Why? Because and average, because if you consider the number of players, to take the average, you need to take the sum over the number of n is the number of player. And that would be average. Good. So as long as n is a constant thing, so sum and average, we are going with the same. So the utilitarian function essentially is the average or the sum, and these are the same. Good. The other one, this egalitarian, this is essentially a measure of fairness. So this essentially one is to try to maximize the sum. Okay, some people may lose in that one, but overall it is good. The other one is the egalitarian version, which is the concept of fairness. What is the fairness? You want to just make sure that whatever you do, the minimum guy has maximum utility. You don't want to sacrifice anyone. Yeah.
So would that be like equality versus equity?
Exactly. So these are like you can have lots of philosophical things again discussion about this one. But in general, one is that you will try to sum of the wealth. The other one is that you want to be fair, like the minimum person gets at least something. And both of them are very reasonable objective function that you can do. Now, of course, we can't define social optimum. So it is, as I mentioned, a good dictator can choose S star that optimizes W, this W is this function that we have mentioned. So S star would be arg max of S Ws. And here I just want to explain this. So when we generally say max is clear, you will take maximum S over all strategies here, all strategy profiles here actually. And then arg max, it means that the particular S that maximizes, we will see this one a lot. Arg max or arg min is the particular strategy, might be several of them, but any of them, that maximize or minimizes this function. So that would be essentially the social optimum. And in some sense, the first one is also called, essentially we try to here maximize the social welfare. Social welfare, or they will say make it efficient essentially. Or efficiency of the system. Efficiency essentially means that we will get this, generally we talk about the sum. As I mentioned, whenever we talk about fairness, we will talk more this egalitarian one, which is essentially minimum expected utility among all players. So this good dictator case I have mentioned, anarchy, as I mentioned, it is like you can think about as a democracy. So here there is no dictator. Every player selfishly try to optimize his or her own expected utility, and they don't care necessarily about the general objective function. Or they may not even have the view of the whole thing. They may not even know what are the objective of other players. Here, we will get generally a strategy profile S, which is essentially a settlement agreement. Or an equilibrium, essentially. Or a stable solution. At least it can be temporarily stable. Of course, in that case, we know that the W of S is less than W of S star. That is by definition. Because S star, we optimize. So this S is just some arbitrary things, and that would be less than or equal to the optimum. Now, what is the definition of price of anarchy? So price of anarchy would be maximum over all S, where S is a Nash equilibrium. You can possibly define this one for any other stable, like, for example, for epsilon Nash, you can define, or you can define it for Pareto optimal or any other, like this correlated equilibrium, any settlement agreement. So this Nash can be essentially replaced by any stable state. For any stable solution, we want to have this one, that the max S of, what is this one? This is the social welfare of the optimum over the social, essentially, welfare of Nash or any stable solution. And we take the ratio, and we take the worth ratio. That is very important. So this is the worth ratio. So in the price of anarchy, we will consider the worth ratio. Why? Because we don't know which Nash we are going there. We want to say any Nash that we are going there, we want to be in a good shape. Or, I mean, we try to be in good shape. Or at least we try to understand it. So whether some Nashes are good or not. If you can design some games that the Nashes are very close to the optimum, generally that's a very good solution. Or have some bounds, essentially. You don't want to be totally off. There is also this concept of price of stability. It's what is the price of stability? This is that POS. That does not say essentially the max, essentially takes the mean. So in the price of stability, you are just taking the mean instead of max. That says that what is the best Nash that we can have it? And still you are somehow comparing to the optimum. Of course, if we have price of stability, we have a better, more essentially, like more robust. Because any Nash, you will go, anyhow, you will go to settlement, you're not far from optimum. But in the price of stability, he said there is only one Nash that if you go there, then you are in a good shape. The whole idea, so then the question is that what is the motivation for one stable thing? Is that, okay, this is one stable. Somebody may suggest this solution to the people and say that, okay, if this is the case, everyone is happy. And you are somehow comparable essentially to the optimum solution. So in some sense, it is between essentially this kind of no dictator and like a good dictator. It is somehow in the middle, this price of stability. So you want to say some good person is coming and suggesting a way. Say, okay, this is the suggesting. I am suggesting this way to you. That you will be a stable. What's the meaning? This you are in a Nash. It means that given that other people are choosing this option that I'm suggesting, you don't want to change it. So you are in a Nash. Even if you consider the selfish things, this is the case. But this might suggest a solution that everyone agrees with, that everyone takes it, everyone is somehow happy. The danger, what is the danger is that somebody, is irrational, that we will talk essentially, want to change the strategy. So why should I do that? I change it. Then if you change it, if the price of anarchy is, price of stability might be very good. Like good means that it's very low essentially, because we take the ratio, like very close to the optimum essentially in this thing. But if somebody change it, then you may change and go to another Nash equilibrium, and that Nash equilibrium can be very bad. So these are a lot of actually literature about price of anarchy and price of stability that we talk more like in more graduate courses, but please feel free essentially to think about it. And there is a generalization I just want to mention briefly. This is the thing that we have started, and there are several works on that one. Then you can consider somehow, this is coming essentially connecting game theory to machine learning. If these people, you may think about that instead of doing a Nash equilibrium, you can define the other thing. So these people try to find essentially find good and find essentially an equilibrium through, Nash. They try to find the best response. But you can think about these agents are actually a regret minimization agents. Well, so this is the definition of regret minimization. So regret minimization is actually these agents, if you are in Nash, also your regret would be zero essentially, because you are doing best response. But so Nash equilibrium is also some equilibrium under regret minimization players. So in the regret minimization player, each of these players, they are doing in a round. This is the multi-round games. And each of them, they try, this is not like one shot simultaneous. This is a multi-round things. And the people, all the time, they try to find something which has the best regret for them. And again, you can see that the Nash equilibrium, if you are a Nash equilibrium, that's also an equilibrium under regret minimization algorithms. Then we have things also called price of total anarchy.
That should be the absolute worst.
This is when it is anarchy, then essentially means total worst. But when these players are doing essentially this in a repeated game, they are playing regret minimization. And again, regret minimization, this is like another whole class that I can talk about it. This is important thing in the reinforcement learning. It is used a lot, essentially. Like essentially, you will hear bandits, regret minimization, etc. And these are the things for the reinforcement learning, essentially, for the repeated games. And you can read more about them, or you may take other classes that they talk more about. So it is beyond that. But this would be a special case of anarchy, and that is called price of total anarchy, actually, that we introduced, actually, this, and the people are using it. Good. POA is, probably one of the most popular one. The price of total anarchy is another one. Price of stability, also the people consider it, but a bit less, because as I mentioned, if one person is irrational, change the things, then everything will change, essentially. And in all of this, we try to find price of anarchy, price of total anarchy, or price of stability. We try to find something which is close to one. We want to get as close as possible to the object. Good. Great. Yeah. So as I mentioned, these are very general concepts. And this price of anarchy and price of stability and price of total anarchy, these have been done more with the people in computer science. So these are more from computational side, that the people have actually done this contribution to the field. And this is exactly the combination of computation plus game theory, which is essentially econ. Good. Like clear all. Good. So let's discuss essentially this one, the price of anarchy. And again, the price of anarchy, price of total anarchy, price of stability, there are lots of papers. You can have a graduate course and then talk about maybe, I don't know, a third of the course just about the price of anarchy and these things. So, I mean, again, this is some introduction, essentially, to computational game theory. Good. So here, consider the price of anarchy in this case. So in the chocolate game or the carrot game that we discussed, so here, a utilitarian welfare function, you try to get average expected utility. What is the best average expected utility here? You can just essentially think about this. And also, this is important. Again, the same thing that I have mentioned. Is it possible that a mixed strategy, so if you want to get the optimal solution, should we go among mixed, or we can just focus on pure ones? Yeah.
I would assume that would be pure because I don't remember the exact things, but I think it was mentioned in some previous lecture that a pure strategy that is optimal is better than every possible optimal mixed strategy.
Yeah, so in general, so this is this idea of this, I will call it the GPA paradox that I have mentioned, that like essentially the one that, I mean, if you want to talk about the sum of these guys, I mean, every like mixed one would be some kind of not better than the best one that you can get it, essentially the pure one. So here you can just go among pure one and find the best one, which is in this case would be this one, 3, 3, the average would be, so the sum would be 6, the average would be 3. And there is no difference. You can consider the sum or you can take the average. So here in the anarchy case, essentially it means Nash equilibrium, then it would be 1, 1. So in that case, the price of anarchy would be W of S star over W of S, which would be just 3. What about if we wanted to use the egalitarian welfare function? So essentially we wanted to find a fair solution. So in that case, in the fair solution case, again, this is actually a fair solution because each of them gets 3. This is not fair, or this is not fair in some sense. But this is a very fair solution. Both of them get 3. Actually, the minimum you can get is 3. So even in this particular game, not all the time, in this particular game, actually, if you want to do it, if you think about egalitarian welfare function, again, this would be the optimum. For your Nash, again, you have 1, 1, which is the minimum is 1. And then again, you will also for Nash, you will consider the minimum and you will compare it, and that would be 3 again. So no difference in this regard. And just one thing, what would be the price of stability in this case? If we consider the, yeah.
What? Because if we on top of the results, then one
Yeah.
I think it would be 3 as well because we're looking for Nash equilibrium.
Exactly. Because we are here still in the price of stability, we care about Nash equilibrium. The one that optimum is the optimum. We don't care about Nash or anything. This is the dictator solution. But whenever we talk about the price of anarchy, we say that among all Nash, what is the worst case? Because at the end, you may end up in any of this Nash. In the price of stability, we say that the best Nash, but still it should be a Nash. The issue is that 3 is not a Nash. So we need to still go with 1 on 1. And so here in this actually price of stability and price of anarchy, both of them are equal to. So not much difference. Price of total anarchy would be a bit harder so that you can think about it as a, like an exercise. And you need to read about, of course, the regret minimizations. Good. Now, sometimes this one all the time, this thing that we are talk about maximizing a welfare function or social welfare. You may consider actually sometimes minimizing the cost. So minimizing a cost function. This can be weight or I don't know, cost or anything. Like for example, the example would be prisoner's dilemma. That you try to minimize the number of years that the people go to prison. In that case, we need to consider the minimization version of that. Everything essentially will be reversed. So we will just go there, I mean, quickly. So utilitarian function, we will consider still average expected cost. So that's the same thing. So average expected utility versus cost. Here, egalitarian version, instead of mean, we will consider max. Because you want to say that you want to get the fair solution, the maximum you want to be minimized. Like the maximum number of years in jail you want to minimize. The social optimum, it would be arg mean of this. And the anarchy, everyone essentially goes selfishly try to minimize his or her or their own cost, disregarding the cost of others. So you want to get a strategy profile which is stable. And in general, now we have the reverse. We know that the C of S, cost of S would be greater or equal to cost of any, the cost of any S would be greater than or equal to cost of optimum, in particular when S is a Nash equilibrium or any stable solution. And all this price of anarchy, it is would be essentially the same thing. So instead of before we took essentially here is still the max. So we will take the max of S is a Nash equilibrium. So this is the same as before in the price of anarchy. The thing that is different is this part. Before we had C of S star over, or like the W of S star over the W of S. Here we have the reverse of that, 1 over that. So still the price of anarchy would be greater than 1. Good, because here, if you see, we have the W C of S over C of S star versus in the previous case. See here, we had W of S star over W of S, but we had a still max. So the ratio still, we take the worst ratio, the price of stability, everything the same. The only thing is that the ratio would be different. Why? Because in some sense, we would like to say that we want to get this price greater than 1. Because like otherwise, if you don't define it, you don't want to say price is half essentially. It doesn't mean anything. Price is generally greater than 1. You need to pay a price. And that is greater than or equal to 1. We always try to get it equal to 1. And that's the thing that we are changing essentially the definition. So maximization and minimization is a bit different. This is the same thing that also defined for an algorithm, is an approximation algorithm that finds a solution. Now, if this solution, if you try to maximize the approximation factor, essentially, always we try to get either to minimize the cost or maximize the benefit. You try to get an approximation factor which is greater than or equal to 1. And we always wanted to get it essentially closer to 1. And here you can see this one in the in this case, that for the prisoner's dilemma, if you consider it, then you can see again here, now you try to minimize the stable. So this one, essentially the optimum solution here for the utilitarian is the one that try to minimize. It would be 1 year in jail and 1 year in jail. But the Nash equilibrium would be 3 years and 3 years in jail. Sorry, what was that? No. So here, this is everything is reversed. So this is like 3 and 3 means 3 years in jail. So and 1 year in jail. So that was the definition. So this 1 year is essentially the optimum because it's 2 or like average 1. But this 3 and 3 was the Nash equilibrium. Both of them cooperate essentially with police. And that, again, you are paying a factor 3. But anyhow, this is just min-max and this. Good. Now let's go to an interesting thing. This is also another. Yeah.
For that version of versus lemma, could we just multiply all the values by -1 and then over the original problem again?
Yeah. Generally, essentially, this is the case for maximization problem, or if you want to make a maximization problem and minimization problem, you can always do 2 things. You can multiply. You can multiply everything by -1. Then it makes a max mean. Or you can inverse everything generally if this is not 0. You can also consider 1 over so you can also make it a 1 over. So everything essentially, instead of like, for example, 3 becomes 1 over 3. These are the 2 typical ways that you can make maximization, minimization. So in some sense, we have done the same thing here. For min and max, we have done just the reverse of it. Everything is good. Good. Braess Paradox. That's something that is very important. So, what is this one? Consider this scenario. You have 1,000 drivers that they want to travel from S to D, a start and destination. There are 2 possible paths here, SAD and SBD. Good. Now, what are these roads? These are like essentially natural problem or practical problem. The road from S to A is long. It takes 50 minutes. It's a highway, but it is very wide. It means that it takes 50 minutes essentially independent of how many cars are there. Or as long as the limited number of cars is there, 50 minutes. The highway that is a beltway in some sense. Not this beltway that we have it here, but that has lots of traffic. Now, the same for the road from B to D. Road 50. However, now we have the road from A to D. This is a shorter one, but it's a narrow road. It's not a highway. How long does it take? The time is number of cars over 25. So depending how many cars are there, in general, the time that it takes would be the number of cars over 25. So this was constant independent of the number of cars. Here, this is somehow dependent. What would be a Nash equilibrium in this case? So in Nash equilibrium, essentially, so you can consider the drivers, a driver that wants to go. So there are lots of drivers. Say, I don't know, as I mentioned, there are 1,000 drivers. All they want to go from S to D. There are 2 options they have it, or 2 strategies, or 2 actions, 2 pure strategies or action they have it. They can either go from the SAD or SBD. So a Nash equilibrium would be like this one. 500 cars are going. So let me just. So a Nash equilibrium would be something that 500 cards are going through this path and 500 cards are going through this path. So let's see what is the time here. So the time here, for this guy that I go for, this is essentially symmetric. So we can only compute for one of them. So this one would be 50. And then here we have 500. So that would be essentially, so the 500 cards are going. What is the time? Would be 50 plus 500 over 25, which would be essentially 70. Good. So that is one way. This is one strategy. So this 1,000 card, yeah.
It appears that any Nash equilibrium will just be equal number of cards goes to both of them, like no matter how many there are. So like if
yes, I mean general, yeah. You can just, this is a general thing. If you have n card, that they should go essentially equally. And why is it a Nash equilibrium? We need to say why with the Nash equilibrium. So essentially say this is 500, 500. Here, it would be not a Nash equilibrium if one of these cards, in this case, want to change it. So if one of these cards want to change it, so it goes to the other one, it needs to still pay 50. But the issue is that, so what was the definition of essentially? So here, note that this is actually, it is interesting. This game has like essentially lots of players. It has 1,000 players. Each of them have two strategies. So if you really want to consider all possibilities, the size of the table would be how much?
2 to the 1,000.
2 to the 1,000 if you want to consider normal form game. That's the thing that we consider the implicit form that is represented by this network, but we can analyze that essentially. But if you want to do it in that form, it would be huge essentially. But we can still analyze this game and say that if this is a Nash equilibrium, why? Because if any of these players, because the strategies are simple, if they want to change it, then they will go, still they need to pay this $50 one way or the other. But if they go here, then the number of cards here, this is 500. One of these guys want to go here. So then here would be 500, 501. Of course, here would be less, but we don't care about that. This goes there, just this T part, it would be 501 over 25. It would be a little bit more than 20. So no one wants to change it. And you can think about it. I mean, this is the only Nash equilibrium for this game, because in general, you can, I mean, try to analyze, say that, okay, these are the strategies. What is the fraction that goes up? What is the fraction that goes down? That you can define. And then you can say that the only way is Nash equilibrium if it is 500, 500, essentially equal. So this is a Nash equilibrium. So far it's good. So there is no concept of paradox here. Like, what is the paradox? So,
real example for what's happening in New York City or something.
yeah, so we will talk about them. Yeah.
Streets.
Yeah. So let's do this one. So this is the thing that we have, actually, we already talked. Now this, let's do this one. I mean, a current government of that city or that place, essentially. So I want to help. I want to add a very short and wide route between B and A. It is short and it is wide. You can think about some kind of bridge, essentially, or under some kind of tunnel. Very good, I mean, essentially, tunnel between these two things. This was a sea before between them, and now this is a tunnel between them. See what will happen in this case. In this case, actually, the Nash equilibrium, again, you can compute it. It's that all these 1,000 guys, all of them, they should go through this path. So the Nash equilibrium here, all 1,000 guys will go through this. Why, again, it's a Nash equilibrium? Because if any of them wants to change it, what will happen? So this 1,000 over 25, which is how much? Which is 40, correct? any of these cars, if they want to change it, they may go, for example, instead of here, they how much would be the total cost for each of them? Would be 1,000 over 25, which would be 40, and another 40. So it would be 80 that they are 80 minutes essentially is the driving time. But if they want to change it, this 1,000, they want to change it, still they will come to this traffic part. So, and then you need to have, then they are paying 50 essentially instead of 40. So this is again very realistic. I have actually done some, like I was driving today, and this was exactly the case. Okay, there's a lot of traffic here. Should I do I miss the class or not? Okay, maybe you should change it. But said okay, if you change it, still you will come back to this traffic one way or the other. And this is exactly the thing. So yes, you may pass this traffic, but you will go and then maybe longer road, you will take it again, you will come to the same traffic. So at that case, essentially instead of 40, you will pay 50. Yeah.
Wait, so what if I'm just a single car? What if my calculus would be 1 over 25? How would it still be 40?
Sorry, can you repeat?
Like if I do 99 cars from S, B, A, B.
Yes. So, yes. So this is the thing that we discussed. So Nash equilibrium, everything that we are talking about, 1% changing. This is the best response. We don't consider collusion or coalition. These are somehow similar terms here. That multiple agents together change it. Yes, if multiple agents together they change it, that will happen. But this is the thing that generally is quite a stable thing, because you may think the whole world essentially, like the people who are buying from Amazon or doing searching through Google. These people cannot coordinate enough. They can change that. Maybe a few of them, you and your friends can coordinate, but probably that does not change that much for the whole thing. So that's the thing, that it is a reasonable assumption to assume that no one person can change it. But again, this is like the thing, there are some definitions you can consider that lots of people together, they cannot essentially change it. And again, consider all of this in some sense are some kind of modeling of the real world. But the issue is that whether the real world behaves like that or not. And in some sense, for Nash equilibrium, like for the internet, yes, there are some cases it might be not the case. If we talk about the people in this class, maybe 3 or 4 of them can change the whole thing. But if we talk about a large population, they don't coordinate essentially generally. Of course, you can think about it that like Google can play the God role here in the correlated equilibrium, and that gives some routes and change the whole thing, because the people may use the Google a lot. But of course, again, it will be not the case if this is in my hometown, because the people know the road. They don't use the Google, essentially Google map every day. So still, Google even cannot change that. And here, again, we are talking about 1% changes a strategy, comparing everything else is the same. So among these 1,999, if they are the same, I want to change it. Can I get anything better? Again, you can think about that in this case. I mean, this is the only Nash equilibrium. You can, again, consider all possible options. You can say, what is the fraction that goes through this? What is the fraction that goes through this? And what is the fraction that goes through this? And you can say that the only way that it's the case, this one is the one that we can. All these patterns, you can put it X, Y, Z, and essentially compute it and see that you will get the only one that is the all flow should go through here. So what did happen? We try to help. We had put a large, essentially, bridge with a very good set of essential lanes, very wide highway under the sea, under the river. And we make the whole thing worse, essentially, because now these people are paying 80 instead of 70. This is the thing that is called Braess. That's the thing that is become paradox, because you try to help, but you hurt. Or like the government is doing right. Good. So let's see. I mean, this is the Braess paradox that we covered. Now let's see. I mean, so, and here, I mean, you can see, I mean, this new game also we can compute the price of anarchy. And in the price of anarchy, in this new case, if you consider the average expected cost, as we mentioned, this is the cost version. Then the optimum cost still would be the previous case that nobody used this one. Say 500 above, 500 below. But that 500, 500 is not an equilibrium anymore, Nash equilibrium anymore. It is optimum, but not Nash equilibrium. So the best thing is to do it 70 like before, but actually now in this Nash would be 80, and this one, the ratio would be 7/8. There are some papers actually that how much you can make it worse, essentially. And there is some bonds for that. With one, you can do a limited damage, essentially. So this is, so you can say that if I am adding one route, how much I can make the whole thing worse. And there is some limitations for that. It's not the case totally unlimited, but essentially, and there are papers on that, but you can read about that. Like the worst case, essentially, that can happen to classical. Good. And actually, one other thing I need to say, this was just, I think, misspoke. So here, still the 500, 500 is a Nash equilibrium. So 500, 500 is still a Nash equilibrium in this case. But it is, if you consider the price, if you consider price of stability, then it's still one because you can send these people. But if you consider price of anarchy, we consider the worst Nash equilibrium, and the worst Nash equilibrium would be this 1000. So there are essentially more than one Nash equilibrium here. 500, 500 is still one because it is a thing that is good here. But so that was essentially, so that would be like 2070, and then if you are doing this one, it would be 20 plus. So just checking that, I mean, to make sure. So here, if you have essentially, so if the number of cars here is 500, so that this one would be how much the things for that would be 20, and here would be cars number of things would be 20. So yeah, if you want to change one of these people there, essentially, that actually is not clear because then it might be, if this is 500 and this is 500, it might be the case actually if one person is coming through here, it can get it 40 actually. It's not an Nash equilibrium. Yes, sorry. So that was again, so the original thing was correct. Because I think there was something in the slide that made me essentially think. But yeah, the 500, 500 is not a Nash equilibrium. But anyhow, if it was a Nash equilibrium and it was worse than that, it is not a Nash equilibrium here. But if it was Nash equilibrium, still we consider price of anarchy the worst case, and that's the thing. So that is not a Nash equilibrium. The only Nash equilibrium is this 1000 thing. It was some confusion. My part. Good.
So yeah, so it starts with one person switching and then every one of them switches.
Yeah, exactly. And that's exactly the problem. So, okay. So the question is that, okay, we have done these things. So this is like the, yeah.
If we assume that it's not possible for all of them to switch, like just one switching at a time, if we reach a point here, it's like the middle of the same time, 2 weeks. So that would be
I think not only that, we have enough. So like you need 2 times 50 times 25 cars for this case. How much that would be?
Yeah, so you need to, I mean, just do, I mean, calculations, essentially. You should do it. I mean, everything that I mentioned, in Nash equilibrium, we talked about 1%. If you say more than 1%, then you can essentially, or if you, I mean, you can see that in this case, actually one by one, they will change it until everything, I think it will go to this 1000. But you, I mean, you should just compute it. I believe they are actually changing all over, but I mean, you should compute it. Yeah. Yeah.
I remember I saw this before. I think that the way I figured it out was that if there are fewer cars, if there's a below some threshold of cars, everyone's going to go along the SBAD. But once you get above certain amounts, everyone going SPAT is going to be more than 50-50.
Yeah.
And at that point, it sounds
So
like
this is actually what was your question? You had a question.
So the only Nash equilibrium is using the middle row.
What's that?
Nash equilibrium is using the middle row.
Yeah. Yeah, the only Nash equilibrium is the one that's okay. So one thing another thing that we are talking in game theory, and I want to just say it is called dynamics. In the dynamics of Nash, so we not only consider, so here, this is also another thing that was a discussion that actually, like she asked. So here we consider the final thing. This is some Nash equilibrium in the final things. The people say, how did you reach to this Nash equilibrium? That is another story. It is called dynamics of these games. And the issue is that, whether with these changes, you will go essentially to a Nash equilibrium, or you may do actually cycling. You may not even reach a Nash equilibrium. All of them is unclear. And actually, there are some cases that if you do one by one, you want to change it, it may take exponential time to find the Nash equilibrium. And that's essentially the whole idea that I mentioned in Nash equilibrium is p-pad, because the idea it takes that, the people think that even if you are doing coordinated movement, then it would be essentially an exponential time it takes to do that. That is the way that we know that. So the dynamics is that how do you reach to a Nash equilibrium? That we didn't discuss. We said if a Nash equilibrium are given to us, then what we do. But that's the whole, different story that how long would be the path? Maybe it takes forever that people reach a Nash equilibrium. Maybe they don't reach an equilibrium because it can be a cycle and they just change all the time, essentially. And that indeed happened, for example, if they are doing a regret minimizations, you can show that the people in the equilibrium case, the people may just alternate, just one here, one there, one here, one here. So you just change the action at each stage, essentially. So it's not just one action event that you will take. So these are all sorts of things, but this is like, you can read it. This is dynamics of the game, very important, very interesting thing. It's much more complex even the Nash equilibrium itself, and there are several papers, and you can go and read about it. But let me finish this one. So here the question is that whether these assumptions are realistic or not. So for example, we say that A to B, T to 0, regardless of how many cars. Really, so is it the case the road length can be 0? Then if this this essentially S go to A and S goes to B. If this A and B are so close, why S to A is not 0, essentially? But the case, as I mentioned, you can think about this is a bridge, essentially. It was some road, and you have some very good, essentially, underground, essentially, highway that they will put it there. So here, this is the assumption, T equal to 50, regardless of how many cars. Is it really 1,000 lane car? Yeah, but again, it is not the case, but for all practical things, maybe it is like that. Or like it is so large that it is essentially practical is like that. And this other thing, so for 1,000 car, this is interesting. That is actually important for queuing theory. And this is the one issue about this analysis of Price of Anarchy here. We talk about the delay would be the number of cars over 25. 1,000 over 25. This means that 40 minutes per car. But these cars, they are not starting at the same time. So they may essentially go one at a time. So in that case, like the first person actually only takes the length of this road. Correct? This is essentially, so this would be the length of this road, not these 25 things. So these are some, yes, again, you may think about this is the average things that we are considering, but for the first case, maybe it's just very fast. And others, maybe there are some delay for them, and then they are going there. This is a realistic assumption. There are some discussion on that. But again, these are all of this that you can discuss it. We try to approximate the things, the whole model. We cannot take every aspect there. We try to do that, but first we need to understand the things. However, the thing that we can here trust on is that the experiments that the people have done it. So these are like, some of the resources that you can actually read here about the Braess Paradox in practice. There are lots of resources references that you can do, but all it says that this is a real progress. This has been a real paradox, and in practice it was like that. Just these are some of the examples. In 1960, 1909 in Stuttgart, in Germany, when a road, when a new road to the city center was opened, the traffic got worse. It didn't improve until the road was closed. 1990, Earth Day, New York closing 42nd Street improved traffic flow. Seoul, in South Korea, closing a tunnel improved the traffic flow. Exactly this tunnel that we were talking about it. Seoul 2003, traffic flow was improved by closing a 6-lane motorway and replacing with a 5-line long park, essentially. So 2010, in the New York, closing parts of Broadway has improved the traffic law, essentially. And these are all of them about the traffic networks. But of course, the question is that, this can happen in other networks, for example, in the internet or communication networks. You may add something and then it becomes worse. There are selfish, but it's a bit different. It's because these are like, in some sense, computers decide which road they should take it. But in some sense, they are all taking shortest path, essentially, and hot potato. I don't know a particular case that is not reported. Maybe there exists such a thing, but it's not reported. But it can happen potentially there as well. So that's about this one, essentially, that we covered about this price of anarchy, and the price of anarchy can become worse even when you are adding some lanes, and how much it can get worse. And in particular, in general, is that this is the game theory. You should understand that. If you don't know what is going on, then you don't understand. Oh, I try to help. I spent so much money to create such a highway or this tunnel, essentially, this very large number of lanes, and then I made the whole thing worse. And this is the beauty of game theory, that you can analyze it. Okay, I stop here, and then we will continue next time.